This is 2019 IMO problem number 6, and here is a view of this geometry problem. We're given triangle ABC with incenter I. You can also see the circumcircle omega in the picture. The touch point of the incircle is D, E, and R, or D, E, and R respectively. From the point D, we draw a perpendicular to FE, segment FE, and we let it intersect the incircle at R. And next, we draw a R, and we let it intersect the incircle omega at P. And also, we draw two new circles. You can see these two blue circles, the circumcircle of PBF and the circumcircle of PCE, and we let those two circles intersect for a second time at the point Q. Then the claim is that the intersection of DI and PQ meet on a line, on the line through A perpendicular to AI. So basically, if we let them intersect, so I go ahead and extend PQ, say somewhere here they meet, and well, I connect it to AI. The claim is that, or we need to prove that this angle right here is 90 degrees. So rather than proving this, I'll do something else, and I'll just delete that for now. So PQ. So what we would rather do is we will first draw the line perpendicular, and we let it intersect here, the circle. I'll label it as N. So this point of interest that we have, I'll label it as Z. So apparently the claim is that PQZ are collinear, right? So an equivalent formulation here, show that P, Q, and Z collinear. Simply because, that would be an equivalent statement, right? So those two statements are equivalent statements. DI, and that's perpendicular for obvious reasons, DI and PQ intersecting at Z and showing AZ is perpendicular to AI is equivalent of showing that DI and a perpendicular line AZ intersecting and then showing PQZ are collinear. This has advantages for the following obvious reasons. So if I extend AI, obviously it would meet the circle of triangle ABC at the bottom point, maybe to the left of this, so somewhere closer here, I would say, at the midpoint of minor arc BC. So let me label it as M. Clearly an M would be a diameter because this angle here is 90 degrees, and as a result N is the northern point, the topmost point of the circumcircle. Awesome. So and that's pretty much it. So next is we can start inspecting the picture, do some angle chasing, seek some cyclic quadrilaterals if any, and then our configuration. For this solution, I will be utilizing the solution of AOPS user Mark BCC168. Pretty good solution using the mixtilinear incircle. And let me begin, if you would like, before I start with my angle chasing, let me give you a brief review of the mixtilinear incircle, and then we can directly go back to our picture and apply it a few times. We will apply 3 or 4 properties of the mixtilinear incircle. So I want to show you those properties, and then I'll directly apply, and we will hopefully we should wrap it up in less than 30 minutes video time. Okay, so here is a picture. that I have available already. We can start. So this is a picture of a mixtilinear incircle, namely this one, omega A. A circle would have three mixtilinear incircles. Omega A here is such that it is tangent to AB and AC, and it's also tangent to the circumcircle of triangle ABC. You can see that the touch points are B1, C1, the touch points to AB and AC, and the touch point between the mixtilinear incircle and the circumcircle here is at point T. As such, there's also a homothety centered at T, homothety, which is critical for us, obviously. Homothety centered at point T, such that HT would map omega A to the circumcircle of triangle ABC. Obviously, there's a second homothety as well, which is the well-known homothety centered at A, and I'll represent it as H sub A, sending the incircle to, again, the circumcircle of our triangle. Also in this picture, you can see that I already labeled 2 points MB and MC. They represent the midpoints of minor arc AB and minor arc AC. Obviously, MCIC would be collinear because MC is the midpoint of the arc, and I is on the angle bisector. So, and similarly, BI and B are also collinear for the obvious reasons. And now we can go ahead and start our results. The first result is that TB1MC, TB1MC are collinear, and similarly TC1MB, these 3 points are also collinear. And the reason is that simply focus on the homothety centered at T, which maps the mixtilinear incircle to the circumcircle. The tangent point, the tangent line at B1 to the mixtilinear incircle is segment AB. So what will happen is that the mapping of B1 under that homothety centered at T will make that tangency line parallel. But then if it's parallel, it means it is the farthest one. It would be farthest point to AB. As such, it should go through that. It should be a tangency at the midpoint MC, right? So that's a straight line. Okay, that doesn't look like a straight line. That sucks. Okay, so let's try to make it. Okay, there you go. And by the same reasoning, TMC1, those 4 points, those 3 points are also collinear. So that's the first result. Now, second result is that I is the midpoint of B1, C1. So second result, B1, I, C1, collinear, and, well, more than that, B1I equals IC1, and B1I equals IC1, you can simply because of Pascal theorem, and to see that Pascal on hexagon, which hexagon? Well, A, B, well, okay, let me label them without regard to order, and then we can check the order if you want. But MCA MB on one side and BTC on the other. BTC on the other. I'm pretty sure I need to change the ordering here. So the idea is AB intersection MCT is B1, and MCC intersection MBB is I, and AB intersection TMB is C1. As such, by Pascal theorem, because those 6 points are on a circle, B1I C1 must be collinear. And how about the fact that B1I is equal to in length to, so once we establish that these 3 points are collinear, Why would they be equal in measurement? Simply because AB1 is equal to AC1, equal tangents, and also B1C1 is perpendicular to AI, pure symmetry, and because of that we can easily establish that triangle AIB1 and AIC1 are congruent triangles. As such, those two segments measure the same length. Perfect. So our next result would be that angle B1TA measures the same as angle C1TI. They are congruent. C1TI. Well, let's go ahead and draw these two segments first, and then TA as well. There you go. So pause the video if you have to. So that's an interesting result. So do your angle tracing, assuming that you guys already paused it. So let me make some spoilers here. So the result follows directly from the fact that IT is a median of triangle TB1C1, and because it's the median, and notice that AT itself is the C-median of the same triangle TB1C1. Why C-median? Because look at the tangents AB and AC meeting at point A, and that's where we draw TA. So yeah, because IT is median, AT is C-median, those angles must measure the same because they are reflections of each other across the angle bisector. Awesome. So, well, but then recall that this AMC, arc AMC measures C. This one also measures C. That one here measures B. That one here measures B. For that, what it means is that if I extend TI, I should say, it should meet at the topmost point of the circumcircle. Do you guys see why? So because if this angle is C, that arc should be also C. Let's call this point N. Remember that A and B was measuring B, so this one is B minus C. So clearly NC measures B plus C, and BN, arc BN measures C plus B minus C, so which is B plus C as well. So N is the midpoint, and N midpoint of major arc BAC, the arc BAC. So it's the topmost point. But then, implying by homothety centered at T, this point, actually, let me label these 2 points here. Let me label this one as R and this one as R prime. Then this implies that R prime is also a midpoint or topmost point of arc of the mixtilinear incircle, right? So it must be the topmost point of, let's say it like that, is also topmost point, a point on omega A, the mixtilinear incircle, simply because is topmost point, because okay, on omega A, because of homothety HT. Amazing. Okay, so that's really another nice result. And one, I think I have just one more result to show, and then we should be good. And it is the fact that AR prime, if I extend AR prime, notice that R prime was the topmost point of the mixtilinear incircle. Due to homothety centered at A this time, it will also go, AR prime will go through the topmost point of the incircle. So if you will, DD prime is the diameter of the incircle. And moreover, so that's result 4. Moreover, if I further extend this line, say over here, and label this point here as E, E would be what? The touch point of the X circle tangent to BC. So there's an X circle tangent to BC over here. And why is that? Simply because of homothety at point A again, right? The same homothety which takes the incircle to the mixtilinear incircle would also take the incircle to the X circle. So E would be the topmost point of that circle. And just for the record, I'm sure you guys remember that BD is equal to CE, and so, but that's okay, irrelevant in our case. What's important then is the following result. So number 4, and that's really cool. Notice that due to homothety centered at T, if MCA, arc MCA measures C, it must be that B1R also measures C. So let me go ahead and connect B1R. So the arc B1R measures C, meaning this angle over here also measures C. Okay, so this angle here measures C. And by the same token, we can see that because arc NMB measures C, arc R prime C1 would also measure C. So let me go ahead and draw this segment chord here. So as a result, this angle over here is C as well. But then that's really nice result. The 4th result, I claim that B1AR, angle B1AR is congruent to angle C1AR prime, C1AR prime. And simply because of congruence of triangles AB1R, because triangle AB1R is congruent to triangle AC1R prime, AC1R prime. And we already established those two angles are congruent. Obviously, due to equal tangents, AB1 is equal to AC1. And lastly, B1R, the arcs are measuring the same, so therefore B1R and C1R, the chords themselves are also equal. So side angle, side similarity. Whew. So therefore, due to congruence of the triangles, these two angles measure the same. And this is critical for us. So that's everything. All these arguments are reversible. So that's basically one way to locate the center of the mixtilinear, the touch point of the mixtilinear incircle with the circumcircle. All you do is identify the topmost point of the angle the topmost point of the incircle, connect it to A, and then measure the angle, and you measure the angle on the other side. Boom. So that's an alternative construction of the of this touch point. Usually the way that I construct the point T would be to rather draw perpendiculars from B1 and C1 and let them meet on AI, and that would be the center of the circle, and then draw the circle. But that's an alternative construction. Okay, so it's been quite a while now, so let's go back to our problem and let's wrap up our solution. So now going back to this problem, you guys can see that I have a dotted circle here. Let me just move this a little bit up. Let's remember the problem again, because we stated the problem early on. So triangle ABC, I in center, the incircle is omega. We draw from the touch points D of the incircle a perpendicular to EF. E and F are the other touch points of the incircle. So that point here we marked it as R. AR extended meets the incircle at P, PBF, circumcircle of PBF, and circumcircle of PCE. We draw them, we let them intersect at Q, and that's how far we came. Now let me go ahead and do some angle chasing in this picture. Obviously we have two lines perpendicular to FE, so that's something that I will be exploiting, obviously. Let me go ahead and draw RI. I hope that would be sufficient to establish some congruent angles. So RI. So let's check things out. Well, first of all, triangle RID is isosceles. So therefore, this angle here measures the same as this angle over here. But then, due to the fact that RD and AI are parallel, we also have this angle congruent to that as well. So let's write that down. RI equals ID, they are both measuring the in radius, imply angle IRD equal to IDR, and similarly lines AI parallel to RD, well, simply because they are both perpendicular to FE, right? That's all implies by corresponding angles AIZ. Angle AIZ is equal to angle RDZ or RDI. Angle RDI. Awesome. So therefore we have three congruent angles, right? So this is RDI or IRD, I should say probably. So RDI, IDR. Okay, good. So the right hand side are same, the left hand sides are also the same. But also notice that triangle on triangle RID, you have this external angle RIZ, which should measure two times one of these green angles, or let me write that down. So angle RIZ is simply equal to angle RDI plus angle IRD, and well, these are those green angles, but at the same time those RIZ itself can be split into RIA plus angle ZAI, if you will, or AIZ, I should say, AIZ. But then suddenly you just realize that so these two measure the same. However, we have already established that, for instance, DRI is congruent to AIZ, suggesting that RDI and RIA measure the same thing. So that's also a green angle over here. Aha. So what happens next is that if you reflect R across AI, which is the angle bisector of triangle BAC, or angle BAC, I should say, that should be directly mapped onto this topmost point of triangle of the incircle omega. So in that sense, if I could label this point as R prime, R prime is the reflection of R across AI, but it's also the antipode of point D on the mixtilinear, on the incircle, I should say. So therefore, this implies that R prime is on omega. Well, obviously it had to be on omega because the incircle is symmetric with respect to AI, but furthermore, it's the intersection of omega and di, I should say. That's pretty neat. Now, because R prime is the topmost point, so if you extend this, already we established that those two angles are congruent. We have a reflection. R and R prime are reflection of each other across AI. So that suggests that those two angles are equal here on top. But if those two top angles are equal, so further implying that angle RAI, angle RAI is equal to angle R prime AI, so that would imply that the other parts are also equal to each other. So further implying R prime AC is congruent to RAB, RAB. But earlier, recall our mixtilinear incircle construction. When these two circles, those two angles are congruent, that's how you can define the center of homothety, or the touch point, I should say, the touch point of the mixtilinear incircle. And here I don't know, I made a messed up here a little bit. So if I extend ARP, that would meet the point T here. Okay, so T is the touch point of the mixtilinear incircle with the circumcircle. Awesome. So we're done with the first part. So that was quite a lengthy proof. So now in the second part, I want to, this part is quite easy. I want to chase further angles to establish some cyclic quadrilaterals. In particular, I'm interested in, I claim, okay, so let's write it as a claim. I claim that B, Q, I, C are concyclic points, concyclic. And the proof is rather straightforward. So it's just some angle chasing. So if you start with angle BQC, we need to show that it is congruent to angle BIC. So let's go ahead and provide a simple proof, just simple angle chasing. Angle BQC is simply equal to angle BQP plus angle PQC, but then angle BQP is the same thing as angle BFP, and if you will, I can even draw that angle here. So that's equal to angle BFP plus, well, because they are on the same quadrilateral, right? So I think it's clear, right? Angle BQP subtends minor arc BP on that circle BFP, and the same arc is subtended by BFP as well. And by the same token, angle PQC I should say, is the same as PEC. So replace PQC with PEC. And well, that would be equal to, so if you add BFP and PEC, BFP I think is subtending, because of the tangency, is subtend minor arc FP, and PEC subtends minor arc PE, or I should say arc PDE on the incircle. So FP plus, let's write that down, FP plus arc PDE. So it is the sum of these two arcs, which is FPE, right? So BQC. Well, actually half of those arcs, right? Because it's an angle on the circle, not a central angle. Sorry for that. So that's equal to 1/2 that, but this is just 1/2 of arc FPE, and well, if you measure arc FPE, which is quite straightforward, for instance, instead we can write it as 360, well, 1/2 times 360 minus 1/2 times 360 degrees minus arc FE. But then for arc FE, because of this angle A here, you can easily measure these two congruent legs, which are 90 minus A over 2 each. So that would suggest that the arc itself will be 180 minus A. And so if we substitute that as well, 1/2 360 minus 180 minus A, minus is a plus. So that's just 1/2 180 plus A, or simply 90 degrees plus angle A over 2. But that's exactly the measurement of angle BIC, which is a very well-known result. right? So the same as angle BIC, you can easily do some angle chasing. Well, for instance, angle ABI plus ACI. Well, okay, so angle BAI plus ABI and angle ACI plus CAI, they should add up to angle BIC, and that's exactly 90 plus A over 2. So we have established that these 4 points, BQIC, are concyclic points. And let me go ahead and draw the circle. So it will be a little bit messy probably. So let me draw it with green color. And once I draw that circle, okay, so something like that. I don't want to spend too much time on drawing that. Okay, there you go. So well, I can do much better than that, I think. There. All right, so yeah, so that's a reasonable circle. Well, next we can, oh gosh, yeah, so yeah, that circle is giving me a little bit of hard time here. Okay, there we go. Oh my, okay, there you are. Okay, next what I will do is to extend, so I can extend QP. So let's augment the picture a little bit. If you extend QP to meet this circle at say point K, then I have a couple of interesting results. Well, you can easily do some angle chasing, so that's our next claim actually. Well, I can write it right here. I don't think I will need the space anyways. So I can write it as a claim. I claim that triangle BKC is similar to triangle FPE, and it directly follows from angle chasing. And so yeah, I can chase the angles if you want, but yeah, my time is really running out. Okay, so something like this. I don't think it goes through the point M, by the way. That's why I draw it in such a fashion. So if you just chase some angles, for instance, angle KBC, this angle here, is obviously congruent to angle KQC, right? So let me not draw it. But angle KQC is the same thing as angle PQC, but angle PQC is the same thing as angle PEC. So it would be this angle over here. That's pretty neat. Yeah, earlier we established that angle PEC is clearly congruent to angle PFE, simply because both of them subtend arc PDE. That's pretty cool. And yeah, so first angle is already proven, because, well, we already proved that angle KBC is equal to angle PFE. It's very easy to show the other way as well. You can easily show also that this angle over here is actually congruent to this one as well, and angle KCB is congruent to angle PEF, and that's enough to, PEF, and that would be sufficient to establish the desired similarity. Further, we can also show that triangle BIC, that's a second claim. Another claim, triangle BIC is also similar to triangle PRE. Okay, I'll show you the angle chasing passingly, because I think I'm really running out of time here. Do you guys see that angle IBC is half of angle B, right? In a similar way, we can easily show that angle RFE is also half of angle B. The way to see it is, for example, you can make use of this 90-degree angle. So this angle over here, let me label it with probably gray, for instance. So this angle measures, well, whatever it is, it subtends arc FD, which you can easily establish because from point B you have tangents to the incircle, and the tangents are at the points D and F. So therefore it should be quite simple to calculate that angle BFD is just 180 minus B over 2, or 90 minus B over 2. Obviously the arc itself therefore measures 180 minus B. So therefore this angle over here should measure 90 minus B. And as such, this one should measure B, right? In a similar way, you can easily establish, again by simple angle chasing, that this angle measures. So that establishes the desired claim. And now I want you, so therefore in the big scheme, we have established that the following pictures, okay, let me make it 100% again. We have these two shapes are indeed similar shapes. Maybe let's use orange. So I have established that this orange triangle is similar to that orange triangle. And also the, let's pick another color, light color maybe. Yeah, this one. And similarly, this blue triangle is similar to this blue triangle. Awesome. So therefore, when you look at it as a combination, the quadrilaterals are similar to each other. Well, the reason I bring that up is because, so let's write that down, if my pencil would let me. So let's go back to say, yeah, well, why not gray? So therefore the quadrilaterals themselves are similar. So RFPE is similar to RFPE, IBQC, IBQC, and these are quadrilaterals. So maybe let me draw like this, a quadrilateral shape. Those two quadrilaterals are similar quadrilaterals, but one of them is special. This one, RFPE, this one is a harmonic quadrilateral. When I say harmonic, okay, so that would take me probably a long time to explain, but for those viewers who already are pretty efficient, conversant in projective geometry, we can see that from the point A we have two tangents at F and E, and then we have also this secant line ARP, and that's a standard definition of a, this is one of the ways to define a harmonic quadrilateral. RFPE necessarily is harmonic, but because similarity would preserve this harmonic structure, it must be that IBQC is also harmonic. But then that brings to mind, hey, why don't we just draw tangents at B and C to that circle of BIC, to the circumcircle of BQIC? And indeed, if you draw these circles and do your angle chasing, you would see that that would meet at the point N, and it's very easy to show that, obviously, because, the tangency would be 90 degrees. So M is the center of that BQIC, circumcircle of BQIC. This is from the incenter excenter lemma. So we have a 90-degree angle here, and that's it. So you can chase the angles if you want. So it shouldn't be hard to see that this angle here is A over 2. Obviously this whole angle here was C. So as a result, you can calculate this angle as 90 minus C minus A over 2 as well by very simple angle chasing. For instance, earlier we established that AN should measure, I think, B minus C from our earlier, let me see. Yes, it was measuring B minus C. So if that's B minus C, so this one is B minus C over 2. And you can add up these angles now to get the desired angle. So A over 2 plus B over 2 minus C over 2 plus C is A over 2 plus B over 2 plus C over 2, which is obviously 90 degrees, and boom. So, well, but because of the similarity, A, R, P were collinear, it must be that N, I, K are also collinear. Now, this is a beauty, obviously. NIK is also collinear, and I'm running out of colors here. I want maybe purple. So K, I, C. Oh, obviously this line does not go through T, not necessarily, at least, unless it does. I don't think so. Does it go through? Okay, so for the time being, let me just skip that. So K, I, N are collinear. Whew. Okay, let me go ahead and draw it one more time because I'm not happy with my drawing. Okay, there we go. Let me do it again. So it should go like, oh gosh. Okay, so like that. All right. I don't think it goes through T, so that's why I don't care. So KIN. So remember, this is the point I, the incenter of our triangle ABC. And now we are ready to wrap up everything. If M is well, obviously M is the where AI, angle bisector AI, meets the circumcircle. So it's the midpoint of BC. So that was point B, that's C. So that's the midpoint. And as N was the midpoint of major arc BAC, so as a result, I think it's clear that oh boy, those points will be collinear, aren't they? Wow. Were they collinear? Okay, they apparently are. Huh. Okay. Well, notice that MTN measures 90 degrees. Yeah, MTN. Yeah. Obviously, because it was one of the properties that I listed here. I said here that the center of the homothety I and the topmost point were collinear. Oh my gosh. So now not only that, but also K. So all four of them are collinear. That's amazing. Okay, so that's really cool. So but now because MTN is 90 degrees, if you drop a perpendicular here, so that would be really nice, because notice that M is the center of circle BIC, the green circle. As such, MI is already equal to MK, so triangle IMK is isosceles. So as a result, IT here is equal to TK. So those two are congruent. Okay, because I don't have any more space. Before the final result, let me remind you that IP, so I is the incenter and P is the point that we defined early on, is parallel, I should say, to if S is the center of the mixtilinear incircle. Let me make the picture slightly larger. If S is the center of the mixtilinear incircle, then I claim that IP and ST are parallel to each other. So T is this point here. And I think the reason is clear, simply because, well, obviously IP, T are collinear, AIS are collinear, and oh gosh, yeah, S should be on that line, on the angle bisector line, of course, because it is homothetic with respect to, oh gosh, that's silly me. I was thinking why. Yeah, these points are collinear. There you go. Okay, that's also okay. Now, well, yeah, due to homothety centered at point A, right? Due to homothety centered at point A, the homothety that sends I to S will also send the point P to the corresponding point on the mixtilinear incircle, which is T. So as a result, IP will be parallel to ST. And now final. Okay, so we are ready to finish this problem using Menelaus. Okay, so it will be a computational finish. Oh no, it's a highlighter. Perfect. It looks like a highlighter. Okay, so if you focus your attention on this triangle ATN, we know that P, Q, and Z. No, Q is not. Oh, sorry. K, okay, K, P, and Z are on the three sides of this triangle. So if we can show that K, P, Z are collinear, that would establish that P, Q, Z are collinear, and we are pretty much done. Okay, because we already know K, P, Q are collinear, because that's how we were able to get to the point K. Awesome. So just apply Menelaus on this triangle. Just chase the lengths. Okay, so how can I do that? I would probably need to erase this side on the right hand side because it's on record anyways, so that should be easy. So you guys can always come back, and so we don't need any of these anymore. So let me just get rid of all this using my eraser, my pencil eraser. All right, so now the rest of it is just proving using the converse of Menelaus to show that these 3 points are indeed collinear, right? So let's write that down. Using Menelaus, apply Menelaus theorem on triangle ATN, and the 3 points with transversal. I don't want to really use the word transversal because I'm not sure yet if they are equal, but okay, so K, P, Z, or transversal points, let's say. Those points K, P, Z are the points we want to show are collinear. So our goal is to show that, simply show that, for instance, AP to PT, AP to PT, TK to KN, TK to KN. Oh gosh, okay, there you go. And finally, NZ to ZA. And Z to ZA, that product is equal to 1. Okay, awesome, or minus 1. Okay, so this is just equal to 1. We will just do it step by step. Let's start with AP to PT, and this is the most annoying one. Well, obviously AP to PT is simply equal to AI to IS, simply because AI to IS. Recall that PI and TS are parallel segments, and then the following. Now I can rather focus on AI to IS. Notice that now triangle AFI. Oh gosh, I need to draw yet another line segment. Oh gosh, that's obviously, so this angle here is a 90-degree angle, so IFA is 90 degrees. So all you do is from S, the point S, you drop another 90-degree angle. You can label it whatever you not K. I think in my other drawing it was B1. Okay, so let's label it as B1. So now we will focus on these two triangles, right? So we have a situation like this. Okay, so we have this. So we have A, I, S, that's a 90-degree angle, that's a 90-degree angle, and further I'm going to connect, do I even need that? I labeled this one as F, and this one is B1, and I'm going to connect B1I as well. Alright, if you guys do angle chasing, you will realize that this is angle A. So this is 90 minus A, obviously, but because B1 AI B1 is also perpendicular. Remember earlier in my configuration I have proven that B1 AIA was 90 degrees. So this is also a 90-degree angle. Okay, my drawing is not that good after all. So this is a 90-degree angle, suggesting that this is also A, and alternate interior angles, this is A. There you go. All right, so I'm freaking out here. So, oh gosh. Okay, so therefore triangle B1IS is similar to triangle AB1I. No. AI B1IS. B1IS, yeah, that's a 90-degree angle, is similar to AI B1. AI B1. So as a result, yeah, I want to make use of these two. Okay, let's write it down. B1I to AI better be equal to IS to IB1. So that would imply that IB1 squared is equal to ISAI. And now the cotangent of angle A is, well, in our case it's really A over 2, right? Okay, A over 2, let's say. Cotangent A over 2 is equal to, well, it is BI to AI, right? Wait, yeah. So if I apply cotangent A over 2 over here, actually, yeah, A over 2, that would be B1AI, yeah, or IB1 divided by, actually, let me just square it right away. IB1 square to IS square, but IB1 square was just IS times AI divided by IS square. The IS and the square cancel, so it is just AI over IS. So this whole thing is just cotangent square A over 2. Holy. Then we can similarly calculate TK to KN, which is just a double application of power of a point. Okay, so I'll just use this space again. So I got my first result. So for the second result, okay, so for TK to KN is the same thing as IT to KN, because earlier we have established that triangle KMI, well, I didn't even draw that triangle, but somewhere here. Okay, KMI was isosceles, so this segment was equal to that. And as a result, MT was perpendicular and it was also bisecting IK. So Kn, and that's equal to, okay, so now we can multiply both the numerator and the denominator by In. IT, In is just IT times N is just the same thing as AI times IM, the power of a point with respect to point I with respect to the power of point I with respect to the circumcircle of triangle ABC. So this is just AI times IM, and Kn times KT IN. Oh yeah, this time this is the power of point N with respect to the circumcircle of BIC. So therefore this would be just MB squared, because we have a tangent here, we established it earlier. Lastly, and Z to ZA would be equal to, yeah, well, okay, let me explain it as well. So you have, if you draw that diameter here, So NZ to ZA would be the same thing as MI to IA, simply because the diameter is parallel to DIZ, right? Because it's also a 90-degree angle, 90-degree angle here. So that would imply two similar triangles, triangle AIZ and AMN. And as such, we would get the desired result. NZ to ZA is equal to MI to IA. And now if you combine these three results, that should, and multiply them out, obviously. If I multiply them out, we would get that the left hand side is equal to cotangent square A over 2 times AI times IM over NB square times MI over AI. Well, the IA's cancel out because both on the numerator and the denominator. So we have MI square over NB square, but MI is equal to MB as well, because M is the center of the incenter X due to the incenter of the circumcircle BIC due to incenter excenter lemma, right? That's just equal to cotangent square A over 2 times IM square. IM is the same as BM, so BM square divided by NB square. But BM to NB, notice that triangle NBM is a right triangle. BM to NB is just the tangent of this angle, but that angle measures the same as, half of angle A. So this is A over 2, right? So that thing would be tangent A over 2. And because we are squaring, so that's cotangent square A over 2 times tangent square A over 2. And cotangent times tangent is just 1, so squared is still 1. And that solves this rather lengthy, bashy IMO problem number 6. Hope you guys enjoyed it, and looking forward to see you guys in another lecture.